In this video, I want to talk about graphing absolute value functions, and I'm going to work through two examples, but before I do, I want to discuss some of the characteristics of absolute value functions first. Now, if you have studied transformations with parent functions, then what we're going to talk about here will be very straightforward, and you'll see some really nice connections that are going to be made. Okay, so here are some characteristics that I want to discuss, and we have our absolute value function here, and here's the general form. We have f of x equals a times the absolute value of x minus h, and then plus k. So our h, remember, is going to be our horizontal translation, or slide, and k is going to be our vertical translation, or slide. And our vertex is given by those two translations. We have the vertex as an ordered pair, hk. Remember, because the absolute value function creates a V graph, we have an axis of symmetry that's a vertical line, x equals h, and that means the left and the right side of the absolute value function will be symmetric to one another with respect to this vertical axis of symmetry. Okay, so our a value out here plays a couple of roles. The slope of those legs that we just talked about are going to be plus or minus a, and that's just the value out front here. And of course, if a is negative, it means our absolute value will open downward. And if a is positive, it means it'll open upward. So let's go ahead and look at our first example. Here we're going to graph the function f of x equals 3 times the absolute value of x plus 1, and then minus 2. So as we stated, and I've written up here, the vertex is hk. And of course, inside the absolute value bars, we have x minus h. Well, that's interesting because it looks like a plus right here. So what I can do is I can change this to a minus to force it to be a negative, and then I'll have to write it this way. So instead of x plus 1, I really have x minus a negative 1. So that indicates that my h value then is negative 1. And of course, as we can see, our k value that runs out back here is going to be a negative 2. Okay. And our a value is the only other value that we care about. It says a is 3, and we know a couple of things about that. That means the slopes of these two legs are going to be plus or minus 3. And since a is greater than 0, we know this is going to open upward. Okay, so lots of information here. Let's go ahead and put it all together and graph this thing. So our vertex is hk, so our vertex will be negative 1, negative 2. So let's go ahead and graph that, negative 1, negative 2, right here. We can put a little v for our vertex. We know this is going to open upward, so we're going to go up this way, and our slopes are plus and minus 3, because we had this horizontal compression by a factor of 3, which is going to squeeze this v and make it a little tighter. So what we have is from here, slope upward, 1, 2, 3, and then over 1, 1, 2, 3, and over 1. And similarly, we can do it across this axis of symmetry, which runs along here. And we can go up 3 and back 1, up 3 and back 1. And so here we have a few points, and you can see it's kind of made a V shape for us. So I'm going to grab a straight edge, and I'm going to go ahead and start at the vertex, and then go upwards this way. And I'll put an arrow on the end, indicating that that line continues forever. And I'll do it on this side as well. Okay, so let's go ahead and do a little conclusion here. Here's what our graph looks like. We have our vertex at negative 1, negative 2, and we knew that would be because the vertex is at hk, negative 1, negative 2. And because our a value was 3, we knew our slopes were going to be a positive 3 and a negative 3. And of course, these are symmetric. These two sides are symmetric to one another about this axis of symmetry. And I guess we could say that the axis of symmetry is x equals negative 1, because our axis of symmetry is x equals h. Okay, so there's our first example. In this second example, I've written our general form for our absolute value function, and again, the notion that our vertex is going to be at hk. And the function we're going to graph here is f of x equals negative 2/3 times the absolute value of x minus 2 plus 4. So let's go ahead and get values for a, h, and k. And it looks like a is going to be that negative 2/3. h, let's see, x minus 2, so h is 2. And k then is going to be this positive 4 that's out back here hanging out. Okay, so the fact that A is negative indicates that this V shape for our absolute value graph is going to open downward. Additionally, because it's 2/3, I know the slope of these two lines are going to be positive and negative 2/3. So we have a stretch here because the absolute value of A is between 0 and 1. So our vertex then is going to be HK, so 2, 4. So let's go ahead and put all this stuff together. So 2, 4, right here is our vertex, put a little V right there. And also we could say the axis of symmetry here is going to be this line, x equals 2. And so we know these two legs are going to be symmetric to one another about this line. So let's go ahead and use our slope, this 2/3, to go ahead and draw some more points that are going down from this vertex. So down 2 over 3, we can do that just the once because then we run out of the graph. And down 2 and back 3, and again we know that it's just going to be symmetric. So down 2 and back 3, and then we can't do that again. Okay, so let's get our straight edge and go ahead and draw these lines in. Okay, so here, this left leg is 1, and then let's go ahead and turn it a little bit and do our right leg. Okay, there's that, and here's my arrow on the end, and again those arrows just indicate that this continues on forever. So this is what this looks like. We have our vertex at the ordered pair 2, 4, and we're opening downward because our A value was negative, and we do have a bit of a stretch because it's opening up a little bit wider than what a typical absolute value function does. So here is our second and final example for graphing absolute value functions.